Is my screen, is the screen visible now?
Yes, Professor. Yes.
Okay. First of all, I'd just like to express my concern or thoughts for the millions of families who had suffered from COVID-19. We would all be, of course, much happier if we could meet in person rather than meeting by Zoom. But I thank the organizers for inviting me for giving a Zoom presentation at the meeting of Society of Special Functions. So this is joint work with Atul Dixit, my former student, and his student, Raja Gupta, and my colleague, Alexander Zaharescu. Yeah. So let me give pictures of Atul, and this is Rajat. So Rajat visited us for a few months 2 years ago. Those of you who are familiar with Urbana realize that this picture was not taken in Urbana. In Urbana, the largest bodies of water we have are pools and backyards. We don't really have any large body of water in Urbana. And this is my colleague Zaharescu. So the main impetus for our paper is, or our research is a rather famous paper by Chandrasekhar and Narasimhan, Hecke's functional equation in arithmetical identities, published in Annals of Math. It actually served as the main motivation for a PhD thesis a couple years ago. So let me define the general class of Dirichlet series and the arithmetical functions that we will be discussing. So A of n and B of n are any two sequences of complex numbers. And we define Dirichlet series phi of s and psi of s in this way. Sigma sub A is the abscissa of absolute convergence for the first series. Sigma sub A star is the abscissa of absolute convergence for psi. And the sequences lambda n or mu n are positive numbers. They tend to infinity. And we assume that phi and psi have analytic continuations into the entire complex plane and are analytic on the entire complex plane except for a finite set of poles. Actually, Chandrasekhar and Narasimhan relaxed this condition a bit. However, in all the examples that we have, we just have a finite set of poles. And furthermore, we suppose that there is some positive number delta such that phi and psi satisfy a functional equation of this type. So let me give several examples to illustrate the general definition and the functional equation that arises. So the Riemann zeta function is the most famous example. So this is the functional equation as it's normally given. In the definition that I gave you, it would be gamma of s would be the gamma function is multiplying the Dirichlet series. So we really have to replace s by 2s. So delta then would be a half. A of n and B of n are 1. Lambda n and mu n are half n squared. The half arises because, in fact, in the definition, we have 2 pi to the minus s power. And then sigma a, sigma a star are both equal to a half. Here's a second example. Ramanujan's tau function, tau of n, is defined in this way. You just take q times the product 1 minus q to the n to the 24th, and the coefficients are the tau function of Ramanujan. If you form this Dirichlet series, it converges absolutely for sigma greater than 13 halves, and the function satisfies this functional equation. So you can see that in this example, delta is 12. A of n and B of n are both tau of n. Lambda and mu n are both n, and as I indicated, sigma a and sigma a star are both 13 halves. So here, chi of s, the left-hand side, is actually an entire function. Let me give a couple more examples. We'll let R k of n denote the number of representations of the positive integer n as the sum of k squares, k greater than or equal to 2. So let me just give an example. R2 of 5 is equal to 8. So you can write 5 as plus or minus 2 squared plus or minus 1 squared, and then you can invert the order of these summands. So there are 8 different representations of 5. So what I've said here for k equals 2 applies to general k as well. We count different signs in different orders as being distinct. So here the Dirichlet series, which I called zeta k of s, satisfies this functional equation. So here, as you can see, delta is equal to k over 2. A of n and b of n are both rk of n. Lambda n and mu n are n over 2, again, because we don't have the 2 out in front, so to speak. And then sigma a and sigma a star are both equal to k over 2. And if sigma, for another example, if sigma k of n is the sum of the kth powers of the divisors of n, then this is generated, these arithmetic functions are generated by the product of zeta of s and zeta of s minus k, where zeta is the Riemann zeta function again. So for k odd, then we have a functional equation for zeta k of s and this type. For k even, we do not get this functional equation. See, note that we're multiplying two zeta functions together. So we'll have a product of two gamma functions, but you need to coalesce, so to speak. So they do if k is odd. And so we get, as you see, one gamma factor. But if k is even, we don't get the functional equation of this type. Yeah. So here delta is k plus 1, a of n is sigma k of n, b of n is a minus 1 to the k plus 1 over 2 sigma k of n. Lambda n and mu n are both equal to n. So a theta or modular relation is a relation of this type. And Chandrasekharan and Narasimhan showed that this relation, a theta or modular relation, is equivalent to the functional equation. So in other words, if you have a functional equation of the corresponding Dirichlet series, then you get a theta relation like this. And if you have a theta relation, then you can get a functional equation of the corresponding Dirichlet series. So in a theta or modular relation, say we have an x here, so usually it would be z, a complex variable. And then here we have 1 over x. So this is, so to speak, the characteristic identity for a theta or modular relation. And then this p of x is this integral. And remember that chi is the left-hand side, so to speak, of the functional equation. Yeah. Okay, and the functional equation and the theta relation are also equivalent to what is called a resum identity. So J nu is the ordinary Bessel function of order nu. Assume that x is greater than 0, and rho, a parameter rho, is greater than 2 sigma a star minus delta minus a half. So remember, this is the abscisive absolute convergence for psi, and this is our translation number, so to speak. So again, the functional equation is equivalent to this identity. So this is called a resum, sum of this type. And so we have on the right-hand side an infinite series of ordinary Bessel functions. And then this Q sub rho, defined on the next slide. But let me just say this prime on the summation means that if rho is equal to 0, and x belongs to the set of lambda n, then we count only 1/2 of a of n, or that is when n is equal to x in our sum. Okay, and this q of x is again a contour integral, the curve C encircling all the singularities comprising S. So these three identities are all equivalent. So this is what Chandrasekhar and Narasimhan showed. So I want to indicate a couple new identities. So they involve modified Bessel functions. So just recall that k½ is just equal to a simple multiple of the exponential function. So it's the fact that this behaves like an exponential function, or almost like an exponential function in general, that is one half is replaced by nu. This is sort of a key that enables us to derive the identities I'm going to give you. And these identities involve, what we need are some integrals and value, giving the values of integrals involving modified Bessel functions. So here is an integral involving a power, a modified Bessel function, and an ordinary Bessel function. Here we have just a power and a modified Bessel function. Both of these involving the gamma function. Here's another integral that we'll need involving modified Bessel functions on both sides. And then fourthly, we need this integral as well. So I won't refer to these again, but I just want to let you know that these are needed in the proofs, which I will omit, but just give you the theorems. Okay, the asymptotic expansions are very important. So this is the familiar asymptotic expansion for the ordinary Bessel function. And as I indicated, the modified Bessel function has an asymptotic expansion involving e to the minus c. Yeah. So here's the first main theorem. We assume a real part of nu is positive, rho is greater than -1, real part of s is positive. And we assume that these parameters are, the sum of them is greater than sigma a star. Okay, then we have an identity of this type. So now we sort of have something that looks like a resum and then a modified Bessel function. Now on the right-hand side, we have something which looks like a Hurwitz zeta function, for those of you who know the definition of a Hurwitz zeta function. And if I so let me just sort of repeat what I mentioned. We have a sort of an analog of the Hurwitz zeta function on the right side. So you can think of the identity as actually providing analytic continuation of this Hurwitz type zeta function on the right side. And the proof uses the resum identity, which is not too surprising when you see that, in fact, there was an x minus lambda n to a power. And we started off with this condition when we use the resum identity, but very conveniently, because we have this nice decaying modified Bessel function, we can actually get rid of this requirement in our final statement of the theorem. Yeah. So here's the special case when we have that rho is equal to 0. Okay, so this is I think it's an interesting identity because we have sort of a theta type contribution from the k nu plus 1. Here we have a power of lambda n. So in other words, this is reminiscent of a Dirichlet series. And then here we have, again, a Hurwitz type function on the right-hand side. Yeah. So that's the first theorem. So our second theorem is slightly more complicated because we have this power of c squared plus x here. Here's a modified Bessel function. Now we have modified Bessel functions on both sides of the identity. And again, sort of a Hurwitz zeta function type contribution. So again, this series identity incorporates features of Dirichlet series, modular relations, and Hurwitz zeta functions. The proof again uses the resum identity. And just as before, we have to begin the proof with this requirement, but we don't really need it at the end. We can just use analytic continuation. So let's just look at the case when rho is equal to 0. So this is a cleaner formula now. So note the symmetry in this identity. So here the R and C are in this Bessel function. And in this one down here, the R and the C are just interchanged. And remember that in the functional equation, we relate this Dirichlet series at an argument with the translation factor minus the argument. Okay, so here we have then nu, and then over here we have delta minus nu. So remember that delta is in the parameter in the functional equation. So again, it has a lot of nice symmetric features, feature that we have in the functional equations of the Riemann zeta function. And then this very nice symmetry here involving the interchange of R and C. Yeah. And it actually appears also here with the interchange. So we have, if you put it on the left side, an R to the minus nu. And then here, we just have delta minus a minus nu, so to speak, on the power of C. Yeah. So in the time I have remaining, maybe I'll spend then about 4 or 5 minutes giving some examples. So if you take Ramanujan's tau function, and because chi of S is entire, we get a very simple identity involving the modified Bessel functions. And then the second, well, let me just give you a special case of this identity. This is when we take nu to be minus a half. So we get k 1/2 in our identity. So this simplifies very nicely into this identity in this special case. And then here is the second theorem identity. Again, note the symmetry in R and C in the identity. Yeah. Okay, let's look at Rk of n. So here, the zeta function, zeta k of x has a simple pole at s equals k over 2. And so we'll also get a contribution from this pole and from 0 because the gamma function has a pole at 0. However, if we define Rk of 0 to be 1, then the n equals 0 terms really just correspond to what we get from the pole. So we have this very nice clean identity, and with the two pole terms sort of coalescing to give the first terms of the series on the left and the right-hand sides. This identity was actually proved by the Russian mathematician Popov in 1935. And there's a proof also in a paper that I wrote with Dixit and Zarescu and my former student, Sun Kim. So since I showed you pictures of Dixit and Zarescu, I should show you a picture of Sun Kim as well. So here is the identity involving Rk of n, the second identity then. Okay, this is actually connected with a famous problem, the Gauss circle problem. So the Gauss circle problem asks for the following. If you look at the sum of R2 of n less than or equal to x, it's not difficult, as Gauss showed, that the main term is pi times x, but there will be an error term. And the Gauss circle problem asks for the correct order of magnitude of the error term as x tends to infinity. This is a long unsolved problem, and we're not close at all to solving this problem. So, Hardy looked at this problem, and this is an identity which he used to attack this problem. And in particular, he showed that the error term is omega plus or minus x to the 1/4. So this is a special case, again, when we have the modified Bessel function being just the simple multiple of the exponential function. So this identity was a key identity in Hardy's proof of this result. So you may not be familiar with this notation, so let me explain it. So on the plus side, it says P of x is omega plus x to the 1/4. This means that for any positive constant C1, there exists a sequence xn tending to 0. Oops, I'm sorry, that's tending to infinity. Sorry for the misprint. Such that on this sequence, P of xn is greater than C1 xn to the 1/4. And for the minus sign, that you have a similar result. So what Hardy's result shows is that you cannot get by with x to the 1/4 as a bound for the error term. It's generally thought of that Hardy's result is close to the true result. In other words, the error term is big O of x to the 1/4 plus epsilon. But this conjecture, as I indicated, has never been proved. Well, let's see, maybe I have time for one or two more examples. For sigma k of n, we'll define delta 1k in this way. We'll define sigma k of 0 by this number. Bk plus 1 is the k plus 1 Bernoulli number. Okay, then we have this is our first identity. And this extra term only appears if k is equal to 1. There are three terms arising from poles, but very nicely, two of them just give us the 0 terms of these series. And in my last example, let's look at characters. So if you have an odd primitive character, we'll let L of S chi be the Dirichlet L function associated with the odd primitive character chi. This is a Gauss sum. So the L function then satisfies this functional equation. And these are the parameters. A of n is n times chi of n. That's because we don't have just L of 2s here. We have 2s minus 1 as our argument. B of n is this multiple of chi bar of n. So again, this is the Gauss sum. Lambda and mu of n are both n squared over 2q, and the delta is 3/2. So these then are the two identities that one gets for odd characters chi. And for even characters, there are similar identities, but since my time has run out, I'll stop with this last identity involving odd primitive characters. Thank you very much for inviting me to give this talk.
Yes, thank you so much, Professor Bruce Blunt. I apologize that I got a bit delayed due to some traffic jam. But I joined. Yeah, it's nice to see you, Bruce, and it was a wonderful.
Good seeing you, Elliot.
Yes, yes. I mean, nice to see you, and it's a wonderful lecture. I mean, in such a short time, you could explain those results. It's wonderful. So now, if there is any question from the audience, you can please go ahead. Bruce is there. Yeah, so it seems like, sir, there are no questions. And of course, people, Professor Bruce is always available. So anytime you can contact, he's very kind to the students, and he will immediately, respond. So that's my experience over the years with Professor Bruce Blunt and all his students. So thank you so much, Professor Bruce, and let's give a big hand to
Professor Kalyan, could I enter just for one minute?
Sure, sir.
Yeah, thank you. Good morning, everyone. And good morning, Professor Bruce Blunt.
Hi.
This is hopefully I'm audible. Yes, my voice is not that clear. Yeah. Professor Bruce, I just, a very small question. Just want to ask, this is Rajendra Lekhwar from Mumbai, GN Khalsa College. I just wanted to ask you, Professor, though there are many versions of the formula one, which Ramanujan sent to Professor Hardy, which is nothing but 1 plus this one, zeta, very related to zeta function itself, 1 plus 2 plus 3 plus up to infinity, and then answer is minus 1 upon 12. But actually, one side it is divergent series, whereas another side is minus 1 upon 12. Though there are many versions and there are many people, there are many things like about it, but I just wanted to hear this thing from an expert, like, of your, stature. So if possible, can you just tell me something about it, please?
So in terms of the inversion formula, you're asking?
The question is like, Professor, this one, 1 plus 2 plus 3 plus 4 plus up to infinity.
Oh.
And then answer is minus 1 upon 12, which was one of the 120 questions sent to Professor Hardy by this one, Ramanujan. Yeah.
So, in terms of the Riemann zeta function, this is, so to speak, what you get by taking the analytic continuation and then, plugging in minus would be minus 1 in this case in the functional equation. So of the results that Ramanujan has in his letters to Hardy and in his notebooks, some of the results which look peculiar like this arise from analytic continuation and then plugging in points for which the analytic continuation isn't valid. In other words, the Riemann zeta function has an analytic continuation into the entire complex plane, but it's not given by the Dirichlet series elsewhere. And then a lot of the other cases where divergent series arise are in asymptotic expansions. And Ramanujan was unparalleled in terms of asymptotic expansions. He has many beautiful, deep asymptotic expansions of various types.
Yes,
in his first
yes.
letter to Hardy, Ramanujan actually discusses sums of squares, but there he examines the problem of counting just the numbers which can be represented as a sum of two squares or are squares themselves, rather than finding the number of in each case of representations. So that's a similar problem, but a little, but not exactly the same problem.
Exactly, Professor. Yes.
Point is like, I answered the question.
Yes, sir. Yes, definitely. I mean, many people actually plug s equal to 1 in this one, Riemann zeta function. But generally, my question was like, it is Riemann zeta function is true for S, a complex number S, where the real part is greater than 1. So here people plug S equal to 1, which should not be, I suppose, like, because it cannot give you a result.
Right.
And that is wrong way of using this one, Riemann zeta function. So that was my question. Yes, sir.
Yeah. But Ramanujan knew that the series diverged, but these, it was his way of sort of, it was an interesting fact, but he knew that, this was not valid. But it gives an interesting interpretation for this divergent sum. Yeah.
Exactly. Yeah. Thank you very much. Thanks a lot. Thank you. Thank you, Professor Kalyana as well. Yeah. Thank you.
Yeah. Thank you so much, sir. So now we can give a big hand to Bruce for such a nice talk. And it was really a privilege to have you with our SSFA conference, sir. And we hope that you will continue your association with us.
Yeah. Thank you for the invitation. Glad to be here.
Yeah. Take care, Bruce, and Merry Christmas, Happy New Year. So have a wonderful ending of this year.
Okay. Thank you.
Thank you, Professor. Thank you, Professor Bruce, for accepting your invitation and sharing your thoughts.
Okay.
Sir, Kalyan, sir. Professor Kalyan.
Yes, yes, I'm here.
You have that schedule with you, right?
Yes. I think Professor Basuki is
Yes.
next. Yes, so
Yes.
you can tell me when to start, and then I will.
So it is a continuous session, so you can
Okay.
start.
So I hope Professor Basuki is. Yeah, I can see he's there. So have you already introduced?
No, sir. No.
So you will do it, or I can.
You can do,
Yeah,
sir.
yeah.
Because I am before that. Let me, since you are late, I just wanted to introduce you because I'm
Okay.
sorry for that.
No. I should apologize. It's not you delayed. I mean, I got a bit delayed.
It's okay. Before that, let me have a quick introduction about Professor Kalyan. Professor Kalyan is basically a person in number theory. He has originally from Harishchandra Research Institute, and he's currently the director of the Kerala School of Mathematics, Kozhikode, Kerala, and he's actually he's an expert in his area, and he's a visiting fellow of visiting professor of many international institutions. I'm not taking much time to read all of this, but just to give that he has so many publications, around 100, more than 100 publications, so many books he has written. And on behalf of the Department of Mathematics and the participants, I welcome you, sir, for chairing this session. So you can.
Dr. Dilip, it's a bit too much, but anyway, thank you so much for this introduction, and I'm really happy to be chairing this session where we have such such great mathematicians with us. We just had Professor Bruce Burnt, and now we have Professor K.R. Basuki, and I think Professor Basuki hardly needs any introduction in this area that our conference is going on. He's an expert in all these areas of special functions, partition function, approximation theory, and many other areas. And he's from University of Mysore, and it's really a privilege to introduce Professor Basuki. And today, the title of his talk is on the Gauss PQ and Lambert series identities. He's also an expert in the Q series expansions. Professor Basuki.
Yeah, thank you very much, Professor Kalyan, for introducing me. Thank you very much for your nice words about me. So shall I share my screen, sir? Am I audible?
Yes, sir. Yes, your screen is visible also.
Yes, sir.
So thank you. So title of my today's talk is on Gauss PQ function and Lambert series identity. One minute. As usual, for any complex number A and a Q with mod Q less than 1, so let us define AQ infinity is equal to product n from 0 to infinity 1 minus AQ power n. Recently, that is in 2001, Gauss, in his article entitled Experiments and Discoveries in Q Trigonometry, he has introduced a function pi q defined by q to the power of 1 by 4 into product n from 1 to infinity 1 minus q power 2n whole square divided by 1 minus q power 2n minus 1 the whole square. This is actually is equal to q to the power of 1 by 4 into psi square of q, where psi of q is Ramanujan, one of the Ramanujan theta function, which I'm going to again define later. So after defining this, he has conjectured the following 17 pi q theta function identities. So these are the 17 pi q theta function identities he has conjectured, and this has been discussed by, and thereafterwards it has been discussed by many people. I'm having some problem with my system. Okay, these are the 17 pi q theta function identities given by this one. He has actually conjectured these things. Further, he also actually Botchrai has confirmed, has shown that the equivalency of 3 and 4 of the above identities, and also he has partially proved the 3, right, by using the Q trigonometric identities recorded by Gauss. Okay, and then being he also deduced the identity 11 and 13 by using the certain Q trigonometric identities of Gauss. So the one of the object of this talk is to prove them using the Ramanujan's theory of theta functions. Further, Gaspar also recorded 13, also conjectured or recorded without proof of 13 Lambert series identities. These are those 13 Lambert series identities recorded by them. So some of them gets coincides with the Ramanujan Eisenstein series identities. Okay, but Chinoy actually proved some of them like 18, 19, 20, 21, and 23, and 23, 28 of the above using certain two trigonometric identities of Gaspar. So in this talk, I want Bingye also proved certain identities like 24 and 25. He has verified using the theory of modular forms. So much what Gaspar has conjectured have already appeared in the literature in different form. In fact, they are deducible from many of Ramanujan's theta function identities. In this talk, we will illustrate with an example how these conjectures follows easily from Ramanujan's theta function identities. In fact, with my students, Ithira Sharma and Harshita, we have proved all the proved or disproved all the conjectures of Gaspar using Ramanujan's theta function identities, and the same has been accepted for publication in Hiroshima Journal of Mathematics. So I'll start proving that. Before that, let me recall the definition of Ramanujan theta function. In chapter 16 of his second notebook, Ramanujan defines as a general theta function f of a comma b by f of a comma b is equal to summation n from minus into plus infinity a to the power of n into n plus 1 by 2 into b to the power of n into n minus 1 by 2 is equal to minus a ab infinity minus b ab infinity ab infinity. In fact, this is actually Jacobi's triple product identity. He rewritten them in this nice form like this. So further, he considered the three special cases of this function and call them like phi of q. That's first one is phi of q, that is a equal to q, b equal to q. So he will be able to obtain a summation n from minus plus q to the power of n square, and that has enjoys this product representation. Similarly, psi of q, f of q, q cube, that is summation n from 0 to infinity q to the power of n into n plus 1 by 2. So this is q square infinity by q square. The Gaspar considered this itself as his pi q function, and with 1 q power 1 by 4 extra in this. So the next another function defined by Ramanujan is f of minus q. F of minus q is f of minus q square, that is equal to this one. the series representation, and this is the product representation of this. This is actually equivalent to Dedekind eta function with q to the power of 1 by 4 product in this. So in all these three functions considered by Ramanujan, so one beauty we observe is the first one is a square, the next is the power is the triangular number, and here it is a pentagonal number of this form is a pentagonal number. So this beauty is missing in Jacobi's classical theta function identity. So the next one, for convenience, throughout this article, I will say f of n be equal to f of minus q power n. F of minus q stands for this. So f of minus q power n, that is q power n infinity for any positive integer n. So in this notation fn, I can represent all these in the form of fn. That will be like this. Frequently I will be using in my thesis. One can easily show that phi of q is equal to f2 power 5 divided by f1 square, f4 square, and similarly psi of plus q, c of minus q. So it's an easy thing. One can show it very easily by the simple manipulation of the product representation of the theta functions. So now let me prove some of the identities of Gauss for now. The first identity which I'm going to prove is this is the first one recorded by Gauss by q square by q square divided by q divided by this is pi q square divided by pi q square pi q power 4 minus pi q square the whole square divided by 1 minus pi q power 4 the whole square equal to 4. This is the one identity which I'm going to confirm conjectured by him, but this is actually due to Ramanujan. This identity is actually due to Ramanujan. So let me prove using Ramanujan's theory of theta function to begin with. So a particular case of Ramanujan one-Simon summation formula is this. This can be deduced easily from Ramanujan one-Simon summation formula. Summation n from minus infinity to plus infinity f of z to the power of n divided by 1 minus aq power n is equal to f of minus q whole cube into f of minus az comma minus q by az divided by f of minus z comma minus q by z into f of minus a comma minus q by a. So this is a particular case of Ramanujan's one-Simon summation formula. So in this one, let me replace q by q square in this to begin with. Replace q by q square in this. So then it will be summation n from minus to plus infinity z to the power of n divided by 1 minus a cube power 2n is equal to f of f cube of minus q square into f of minus az comma minus q square by az divided by f of minus z comma minus q square by z into f of minus a comma minus q square by a. Okay, so just I have replaced q by q square in this. Now let me substitute a equal to minus 1 and z is equal to q in this. Put a is equal to minus 1 and z is equal to q in this. Then it will be summation n from minus q to plus infinity q to the power of n divided by 1 plus q power 2n is equal to f cube of minus q square into f of A equal to Z and A equal to -1 and Z is equal to Q means KZ is minus Q. So this will be Q, comma Q divided by F of minus Q, and this is F of 1, comma Q squared, 1, comma Q squared. So by the definition of P of Q is F of QQ. So therefore, this is P of Q, and this term is P of minus Q. And we know that F of 1, comma A is equal to 2 times of psi of Q square. Psi of Q. So let me use those things here. Then it is F cube of minus Q square, and this is P of Q divided by this is phi of minus Q, and this is 2 times of psi of Q square. This is one property of F of A comma B. So now, as I have already told you, shown that these things can be written in the form of Fn. If I represent these two in terms of Fn, and if we simplify this, I am going to get that this is phi square of Q. So by 2. Okay. So therefore, we have, let me transform this to this side. So phi square of Q is 2 times of summation n from minus u to plus infinity q to the power of n divided by 1 plus q power 2n. Okay. So this formula, if we compare the coefficient of q power n of this formula, we will get the representation of a number as sum of the formula for representation of a number as sum of 2 square in terms of a divisor function. And I can rewrite this one in like this. This is equal to actually 1 plus, if I write it n is equal to 0, and then splitting those two, then it will be 1 plus 2 I multiplied. So it is 1 plus 4 times of summation n from 1 to infinity q power n divided by 1 plus q power 2n. So I can rewrite this series in this way. So now let me consider phi square of q minus phi square of q square. So this one will get cancelled. So replace q by q square. I'm going to get the expansion of this. So it will be 4 times of summation n from 1 to infinity q to the power of n divided by 1 plus q power 2n minus summation n from 1 to infinity q to the power of 2n divided by 1 plus q power 4n. So now the even terms of the power will get cancelled, and I will be remaining only with these things. So this it will be 4 times, that is, it becomes 4 times of summation n from 1 to infinity q to the power of 2n plus 1 divided by 1 plus q to the power of 4n plus 2. This is what I'm going to remind after the terms that if I expand it, and even terms will get cancelled. The odd power terms only going to remain here. So that is what it is. So now, again, I will come back to this formula only. Again, if we come back to this formula, yeah, in this formula, if I replace q by q square and setting a is equal to plus 1 and z is equal to q in this, I'll be obtaining the series representation for this, and that will be, and if I simplify the product representation, that will be equal to 4q into psi square of q power 4, psi power of q power 4. So this is what I'm going to obtain. So I've been able to show that p square of q minus p square of q square is equal to 4 times of q psi square of q power 4. So we have this relation. We have this relation, that is phi of q is equal to psi square of q divided by psi of q square. This another identity required by Ramanujan. It follows very easily. So if I use this one here, then this it will be psi power 4 of q divided by psi square of q square minus, and this it will be psi power 4 of q power 4 divided by sorry, psi q square here divided by psi square of q power 4 equal to 4q times of psi square of q power 4. So now expressing this in the language of pi q, this would be pi square, and also dividing by this, and also dividing by this, it is pi square of pi q square divided by, and this will be pi q square into pi q power 4 minus pi q square divided by pi q power 4 square equal to 4. So this is one of the identity conjecture by Gauss, but it can be proved very easily in this way. Similarly, we prove the remaining Gauss identities in a very simple way by using 1/7 summation formula and other steps. Next, I will consider the one Lammers series identities. I'm going to give the proof of one Lammers series identities. That is this. So here's conjecture that summation n from 1 to infinity q to the power of n divided by 1 minus q power n the whole square minus 4 times of summation n from 1 to infinity q to the power of 4n divided by 1 minus q power 4n the whole square is equal to 1 over 8 times of pi q power 4 divided by pi q square power 4 minus 1. So let me prove this one. So to prove this, I require a particular case of W/N basic bilateral hypersymmetric series. I'm not going to write the W/N hypersymmetric series because I'm running out of time. So just I'll recall a particular case of it, that is this. So we have summation n from -1 to plus infinity q by a whole to the power of n divided by 1 minus aq power n whole square is equal to q infinity whole to the power of 4 divided by q infinity square into q by a infinity square. It's a particular case of W/N Bayes, a 2-side basic bilateral hypersymmetric series transformation formula, right? So in this formula, so first let me replace a by a -1 in this. If we replace a by -1 in this, I am going to obtain summation n from -1 to plus infinity -1 to the power of n, sorry, minus q power n divided by 1 plus q power n the whole square, 1 plus q power n the whole square. So this side it will be q infinity power 4 divided by this is also -1 and this is minus q. So -1 is 2 times of minus q only. So it is minus q infinity power 4. Minus q infinity power 4. Or this I can rewrite it like this. In the language of f, it is f1 to the power 4. And this can be written as by using Euler's identity. This is q square infinity whole power 4. But this is equal to f1 power 4 into f1 power 4 divided by f2 power 4. Or this is equal to f1 power 8 divided by f2 power 4, and this is nothing but psi power 4 of q, psi power 4 of q it is. Sorry, it's not psi 4. This is phi of phi power 4 of minus q it is. So therefore, we have been able to show that phi power 4 of minus q is equal to summation n from minus to plus infinity minus q power n divided by 1 plus q power n the whole square. Or I can rewrite it like this. This is n is equal to 1 plus. I've forgotten to write this 2 I'm missing. So divided by 2 I have here. So by 2 I'm having here. So by 2. So using that 2 here. Okay. So it is 1 plus, if you expand the series, it is 1 plus 8 times of summation n from 1 to infinity minus q power n divided by 1 plus q power n the whole square. So therefore, phi power 4 of plus q is 1 plus 8 into summation n from 1 to infinity q power n divided by 1 plus minus 1 power n q power n the whole square. So this is nothing but this implies 1 by 8 times of this p power 4 can be written as by q power 4 divided by by q square, the square minus 1. I'm pushing this. So this, if we this you can write it like this, separating the even and odd terms here, it will be summation n from 1 to infinity q to the power of 2n minus 1 divided by 1 minus q power 2n minus 1 the whole square plus summation n from 1 to infinity q power 2n divided by 1 plus q power n the whole square, separating the even and odd here. So so let me add this term so that I have to make this one from n to 1 to infinity q power n divided by 1 minus q power n the whole square. So minus this summation n from 1 to infinity q power n divided by 1 minus q power n the whole square. So let me add and subtract this. So sum will be goes with this one, and that will make sense. But I'll get this plus retain this term as it is, summation n from 0 to infinity q power 2n divided by 1 plus q power 2n the whole square. So now if I club these two, I'm going to get summation n from 1 to infinity q power n divided by 1 minus q power n the whole square. It will be minus summation. That will be, if you simplify it, I take the LCM, and if I simplify this, it will be minus 4 times of q n from 1 to infinity q power 4n divided by 1 minus q power 4n the whole square. So this is the proof of one of the conjecture given by him. And Ramanujan not exactly written this, but a version of this has been written by Ramanujan also. Similarly, let me do the another one. The last one which I'm going to prove. So the other one is this that I'm going to prove. So this is another Lambert series. By q square, the whole square is summation n from 1 to infinity q to the power of 2n minus 1 divided by 1 minus q power 2n minus 1 the whole square minus 2 times of summation n from 1 to infinity q power 4n minus 2 divided by 1 minus q power 4n minus 2 4n minus 2 the whole square. This is the other one which I'm going to prove. To prove this, I will make use of the one of the Wn Bayes summation formula. So which
Just to interrupt you, sir.
Sure.
The time is
Yeah.
there. So
Okay.
please carry on. Yeah.
In 5 minutes, I went to come. Summation. So this is Bayes summation formula, which he has published during 1951. This is a q power n whole square minus summation n from minus to plus infinity, b cube power n divided by 1 minus b cube power n, the whole square is equal to a into f power 6 of minus q into f of minus ab minus q by ab into f of minus b by a into f of minus a q by b divided by f square of minus a minus q by a into f square of minus b comma q by a. So in this Bayes summation formula, if I replace first let me change q to q power 4 and then setting a is equal to q and b is equal to q square, I'm going to get this formula. This formula will be immediately if we can get this formula. In this way, we can prove all the 13 Lambert series conjecture by Gauss. So I thank the organizer for giving me this opportunity. Sir, I'll continue.
Thank you so much, Professor Basuki. And it's really wonderful that you just derive everything on there, and it's not that an easy task, and it's really wonderful. And since we are just a little bit away from the time, so maybe one question I can allow the audience if there is one question, and then of course people can contact Professor Basuki. Yeah, so let's thank Professor Basuki for this wonderful talk, and
thank you.
Please contact him. He is also another person who will be always eager to respond. Thank you, sir. Thank you so much.
Thank you very much. Thank you.
Yeah, so Dr. Dilip, can you go ahead with the next and the last?
Yes. We can go, sir.
Yeah, I could see
Professor Gaurav is the next person, sir.
Professor Gaurav Bhatnagar is already there, I think.
Yes. Sir, Professor, thank you, Professor Vasuki, for accepting our invitation and delivering a talk on behalf of the department. I extend our sincere thanks to you.
Yes, sir. Yes, so our next speaker is Professor Gaurav Bhatnagar, and he's from Ashoka University. And he's a very well-known person in this area of special functions. And of course, I mean, he has many other areas of expertise, like in hypergeometrics, to be specific hypergeometric series, Q hypergeometric series, and even in number theory. But one of the most interesting for the young audience here will be that he likes to, one part of his research is to look into these Ramanujan identities, these congruences, that beautiful congruences that Ramanujan had proved in a discovery approach. So we are very lucky that today he is going to speak on two of the most popular congruences, one on partition function and one on Ramanujan tau function. And he's going to give us some elementary proof of these two beautiful congruences. Thank you so much, Professor Bhatnagar. And I welcome you and I request you to start your presentation.
Thank you very much. It's a great pleasure to attend this meeting. So the last time I attended it, this society was being thought about. So I attended a meeting of special functions in Chennai in 1997 when we thought that we should have a society. So it's a great pleasure to be here. So I'll just get on with it because maybe try to finish in time. So what we are looking at, what are we looking at? We are looking at partitions. First of all, let me explain what the results are. First of all, for what I'm doing. So partition is a way of writing a positive integer as an unordered sum of positive integers. So for example, let's take 4. This is the way you can write it. So 4, 3 plus 1, and 1 plus 3 is looked at as the same as 3 plus 1. That's what unordered means. So unordered means that 1 plus 3 is equal to 3 plus 1. And then you have 2 plus 2, 2 plus 1 plus 1, 1 plus 1. So there are 5 partitions, and we say P of n is the number of partitions of n. Okay, so one way of looking at them is also through generating functions. And this is the generating function which was found by Euler. So I'll just explain how you get this. So you take 1 over 1 minus q square, 1 minus q cube, then you expand it all in a power series. So let's just do a few. So 1 over 1 minus q times 1 over 1 minus q square times 1 minus q cube times a lot. But let's just expand each one of them as a geometric sum. So this is q square plus q cube, so on, multiplied by 1 plus q square plus q raised power 4 plus q raised power 6 and so on. 1 plus q raised power 3 plus q raised power 6 plus so on. And then there are many terms. And let me just show you how to get q raised to the power 3. So how do you get q raised power 3? So interpret this as 1 plus 1. Interpret this as 1 plus 1, 1 plus 1. And this is 2, and this is 2 plus 2, 2 plus 2 plus 2, and so on. So how do you get q raised power 3? So the first one you get is just this guy multiplied by 1 and 1. So you get q raised power 3. Then you get 1 from here and here. So you can think of it as getting q to the 2 plus 1. And then you get this chap right here. And all others are 1s. So you have 1 plus 1 plus 1. So you can see that you get 3 q raised power 3. So if you expand this and you collect coefficients, you will get P of n, the number of partitions. Okay, so this is, I mean, it's an infinite product, and we saw this product in the previous talks too. But here we don't need to look at it as an analytic object. You can just look at it as something which you can just compute. So, you know, one thing I could do is I could compute using a computer. So this is something which is available for free for all of us to compute. And this is how you compute it. So here I'm just taking 8 terms in 1 minus q raised power minus 1, and I get the familiar geometric sum. Then I add 1 minus q raised power minus 1 times 1 minus q square raised power minus 1. So I take 2 of those terms. So each time I add more terms, some more terms get stabilized, right? So this is stable now. And this is not stable here, but it's stable here, and so on. So using this approach, I can calculate P of n very, you know, at least using a computer, I can calculate. So you can ask, I mean, how, you know, Ramanujan didn't have a computer. How did he do it? So, well, he was a computer himself. And the interesting story about this talk is that Hardy and Ramanujan were working towards a formula for P, and they wanted to find P of n equal to some formula, and they were unable to do it. They were just making guesses, so they wanted somebody to compute. They wanted to compute large amount of values to test their theories. So this was this famous problem, and they got a computer. So the computer's name was Major McMahon. And Major McMahon, what he did was he computed a table of 200 partitions. So we don't have Major McMahon. I mean, you can say Ramanujan himself was a computer, but apparently Major McMahon was an even better computer than Ramanujan. And he computed it. So this is his table up till about 200, which is over here. So this is P0, 1, 2, 3, 4, 5, P5, P6, P7, P8, and so on. And Major McMahon computed this table and arranged it in groups of 5. And immediately Ramanujan noticed something over here. So he noticed that every fifth entry is divisible by 5. So what did he notice? So Ramanujan observed that this is congruent to 0 mod 5. Just because McMahon put it together, Ramanujan just instantly saw this pattern, and that is one of the subjects of it. So this was the easiest one, and then Ramanujan found more and more in these tables, and this is a long area of research, but I don't want to. So the objective is to prove this guy in a very simple manner. Okay, so this is not it. There was one more observation which is related, which Ramanujan proved. So this is regarding the tau function. So Ramanujan had this function. So this we saw in Professor Bruce Burn's talk. Earlier we had 1 over 1 minus q to the k, this product. And now we have 1 minus q to the k. So it's in the numerator, but raised to the power 24. And then those coefficients are called tau function. So for some reason, Ramanujan looked at it. And these are called Ramanujan. This is all Ramanujan's tau. And he got a very similar, exactly the same, almost congruence, that tau of 5n plus 5 is congruent to 0.5. So both these guys, are the easy. These are the ones in the title of the talk. And the only thing, so I'm saying elementary, but I would say it's, it's not really high school, because one result that we use is due to Jacobi, which is not really totally elementary, but it's in the same line. So here it's power 24, here it's power 3, and Jacobi wrote it like a sum where a lot of the numbers q raised per n are 0. The only ones which are non-zero are one where there are, when n is k plus 1 over 2, and there is this coefficient 2k plus 1. So this is due to Jacobi. It follows from Jacobi's triple product identity, and it may have been known to Gauss before Jacobi. It's not clear, but I think it's attributed to Jacobi. So all these three things I should mention is about, let's take this q, 1 over 1 minus q square q, and if I raise it to the power r, some r. So if r is 1, we get partitions. So I'm just calling this notation p sub rn. And if r is 1, I get partitions. R is minus 24, I get Ramanujan's tau function. And r is minus 3, this is the Jacobi story. That when n is this is called a triangular number, because the sum of the first k numbers. So you can arrange them in a triangle. A base into altitude over 2, you can think of it. And so all these three we will use. So in general, we are looking at this. So we are going to prove these two recurrences in this talk. And the only thing we will use is Jacobi's result about this r equal to minus 3, this p. That's all we have to use. Okay, so what are the ideas required for the proof? The first idea is what we are calling the series divisor of a series. So what is it? I mean, you take a series. This is q is equal to some p of n qn. So this is some general. You think of it like a partition or a tau function or something. And if you define sigma q, and I'll explain this notation in this manner. So you take k, p, k, q raised per k, this series, and then this product of series, and you can define sigma q k from here. And in fact, how can you define it? Because just by comparing the coefficients, you get this this kind of recurrence relation. So what am I doing here? What I'm doing here is I'm taking d by dq of log q of x, and then multiplying by q. And then, so when I do that, then I get 1 over qx times q prime of x, which is this guy. Then I multiply by q, and then whatever I get is my sigma q, k, q raised per k. So this is really what I'm calling series divisor. This is a very classical thing which is from Euler's times. You take the derivative, the log derivative. And these coefficients, and it's virtually obvious now that if I multiply two series A and B and take their series divisor, then it will be the sum of the series divisors, because log of A plus log of B is equal to log A plus log B, and then I take the derivative, multiply by Q, I'll get this. So this should be trivially clear. Okay, so but this is really brilliant. Actually, nobody seems to have looked at it quite this way. The reason it's brilliant is that it's so simple that we can use this idea to calculate the series divisors of many series. So let me show you the calculus. So this is the definition again, and let's see what is the series divisor for 1 minus q. So what we are looking at here is 1 minus q, this guy, then this sum sigma q k, q raised per k, and on this side you have k times pk. So pk is just p0 is 1 and p1 is minus 1. So it's just minus q here. So what do we get? We get minus q over 1 minus q is equal to this sum right here. And this guy is just minus q times 1 plus q square plus 1. So what do I get? I get minus q square, minus q cubed, and so on. So I just compare these coefficients are really minus 1, minus 1, minus 1, minus 1, and so on. So this should be clear immediately. This is also not bad. So I'm making some calculations, but they're a lot easier than Vasuki's calculation. So if I want to do this guy, so on this side, I have this sum again, sigma q k, q raised per k. And this is 1 over 1 minus q. And here I expand it as 1 over 1 minus q is 1 plus q square, and then take the derivative and so on. So I'll get k q raised per k. So then what do I get here? I get k q raised per k times 1 minus q equal to this sum. And how do I get this chap? It's just the coefficient of q raised per k. So it's k minus 1. So that's equal to 1 for all k. So this is what I get, 1 on 1. And now for q square, I just replace it with q square. I mean, it's very easy to see that all that you get is 0, 2, 0, 2, 0, 2, and so on. Then q cubed, if you have 1 over 1 minus q cubed, you have 0, 0, 3, 0, 0, 3, 0, 0, 3, 4 is 0, 0, 0, 4, and so on. So, and now I use the calculus. I just calculate this product, the product which we started with, this q cube. If I want to calculate the series divisor, I just calculate it by summing all these. And when I sum these, I get 1s here, then 1 plus 2 in the second row, then 1 plus 3 in the third column, then 1 plus 2 plus 4 in the fourth, and so on. And you can see the pattern. It's sigma 1, sigma 2, sigma 3. Sigma meaning sigma is sum of divisors. So remember, I wrote down a recurrence relation for calculating sigma. If I write that down for this sum, I get this identity. This is a recurrence relation. It says sigma d times p of n minus d is npn, d going from 1 to n. This has been attributed to Ford, and it was used by Erdos to find for some results. But I found it in Bruce's book. I mean, in Ramanujan's notebooks. It's there somewhere early. So Ramanujan knew about this approach of calculating p of n. So I would say Euler would possibly have known this, but Euler already had a way of calculating part. I mean, I should just say that this immediately implies that if I have q raised to the power r and I want the sigma of that, then that is r times q sigma q of k. So just like logs, you can take powers, and this r can be anything. I mean, it could be a real number, a rational number, or whatever. So the other idea number 2, which we use, is that you have a power recursion. So if you take q raised to the power r, and then this was our notation, we used to call it pr of n, then it satisfies this recurrence relation. And this is due to Gold. He didn't use the terminology of series divisors, but I mean, it's all fairly easy. I'll just show you the proof. And what he did was he proved this result for s equal to 1 and or r equal to 1, one of them. But the general case can be obtained from that. So he was considering mostly numbers, but one can change it to rational numbers. And the other person who used a similar result, he used it for s. If you put s equal to -3 and use Jacobi's formula, which I showed you, you get this recurrence relation for PR. And this is due to Lammers. So what was Lammers' interest? Lammers used this formula for the special case when R is minus 24 to calculate. So he had a paper on calculating the tau function. And when R equal to minus 1, R equal to 1, he had, he had this formula for recurrence relation for partitions, which was a little different from Ramanujan. So Lammer had this result and he used it to compute values of tau of n. This was a famous paper in 1940, late 40s and 51, where he calculated many things about the tau function, and that helped in resolving some of the conjectures around it. Okay, so what's the proof? The proof is very easy. It immediately follows that if you're taking q raised per r, then the sigma is r times sigma q, and similarly s. And if you eliminate these guys from these two equations, you get this equation. And you just compare coefficients on both sides and you get the recurrence relation. So idea number 2 was to use this general formula, power recursion, in the special case when s is equal to minus 3, which was, so here is what now we go on to the proof. Okay. All right, so what are we proving? We're proving actually PR of 5m plus 4 is congruent to 0 mod 5 if R is congruent to 1 mod 4. So R is congruent to 1 means R is 1 is allowed and R is minus 24 is included. Both of them are included here. Okay, so we'll prove it in general. And if we look at this Lammers recurrence relation, this is what it looks like. And the proof is by induction. What we do is for m equal to 0, this m0, we just look at what this recurrence relation shows. So what does it show? It says 4 times PR4 is 9 plus R PR3 minus 5 R plus 1. So we are looking mod 5. So this is 0 mod 5. And R is congruent to 1 mod 5. So 9 plus 1 is 10. So that's congruent to 0 mod 5. So we know this is true. Okay, that this PR is congruent to 0. Is that okay? I'm kind of used to people, students showing me their faces and making faces to show whether they've understood or not. But anyway, so okay, so then how do we prove it in general? We just take every term of this guy in general. So when J is congruent to, so for index J congruent to 4 and 5 mod 5, it's something, and it's it's something times PR of 5m plus 4. So by induction, this is 0. So it's a smaller number, 5m of the form 5m plus 4. So by induction, it's 0 mod 4. So this is okay. If J is congruent to 3, then I get PR of something, but over here there is something 2R minus 2. And if R is congruent to 1 mod 4, this is 0. So this is okay. If J is congruent to 2, then I get 5 times something. J is congruent to 1, we get 5 times something. So this is always 0. So term by term, every term in this recurrence relation is 0 mod 5. So PRN is 0 mod 5, and we have for R going from 1 to 1. So the proof is complete. It's not, I wouldn't say it's elementary because it uses Jacobi, but it's certainly easier than the 3 proofs. So I heartily recommend Bruce Byrne's number theory in the spirit of Ramanujan. And it has 3 proofs of the same results. They're not tough, but they look easy, tougher than what we present. Okay, so this is general. I mean, we just proved for R congruent to 1 mod 5, but the same kind of argument can show. We can calculate that if R is congruent to 0 mod 5, then 5m plus 1 is 0 mod 5, 5 plus 2 is 0 mod 5, if R is congruent to 2 mod 5, and so on. So this is actually remarkable that so this is the extensions. It just falls out from this easy proof. There's nothing complicated. So what is interesting here is this guy, Chan, Heng Hua Chan. So this is Heng Watt, and this is Liu Quan. So they are, I would say, Bruce Byrne's progeny. So the student and student. So both from Singapore. I mean, Liu Quan is from China, but he studied in Singapore, and Heng Watt is in Singapore. So what they have done is, so we looked at 1 over 1 minus q square, and so on, raised per 1 minus q raised per whatever, raised per r, right? For r equal to 1 minus 24 and minus 3. What Heng Watt and Wang did was they looked at congruences for r rational numbers. And then they used, they experimented and found many congruences. And some of them, for rational numbers, and some of them are covered here. So about 7 or 8 are covered here. So they found many more, but they found a finite number. And what we have is an infinite set. We have an infinite family of congruences for these powers. So some of them are covered. Some of these guys' work is covered. And similarly, we can, they didn't consider mod 3. I mean, this may be trivial. So similarly, we can have for congruent for mod 3 results. PR 3n plus k is congruent to 0 for both k equal to 1 and 2. And before finishing, I should say that this approach works for many other things. So we can start with other products. For example, we started with this product. So this is another theta function, which can be written in terms of, sorry, I'm writing as well. So there's triangular numbers here. So this is also a theta function, and it's well known that, so these are triangular numbers. So we can use powers of these. These can also be written as products. Okay, so we can just do the same kind of calculation, and we get a result for sigma of n, the sum of positive divisors of n. We take sigma n 0 if n is less than equal to 0. So if 5 divides n, then sum of the sigma of 2n plus 1 minus this number is congruent to 0 mod 5. And if n is for mod 4, we got n not equal to a triangular number, then this thing is congruent to 0. So there are many more which we found using exactly the same approach. We used this product rule and so on. Okay. Yeah, I hope I've finished in time. Thank you very much. So I should mention that my collaborator Hartosh Singh Bal is also in the audience, I think, and he's so we've been working on these together. Okay, so I'm done. Thank you very much.
Thank you so much, Professor Gaurav, for this very interesting talk. I'm sure a lot of these participants, young and even the people who are experts, will be looking into these identities. That the idea that you have given, it looks very interesting. So, if you have any questions from the audience, we can take a few questions. Professor Gaurav is there. Yeah, so it doesn't seem like that, Professor Gaurav. So let's give a big hand to Professor Gaurav for, I also share with him that, we used to see the faces of the students and the audience where you see whether somebody is understanding or not. But this is the era that we are living in. We have to get used to these things. I think it's going to go for a long time. So thanks a lot, Professor Gaurav. It was really interesting talk and really fitting for this conference. And thank you so much for accepting our invitation to give a talk in this SSF. Thank you so much.
Thank you.
Thank you, Professor Gaurav. On behalf of the department, I extend sincere thanks to you for delivering this lecture. Dear sir, can we have a group screenshot of all the participants together with the video on, so that
yeah, sure. That will be a good idea.
Please,
yes.
I request each one of you to switch on your video so that we can have a group image of the sessions. Many of them are switching on. I request each one of you to switch on your videos. Still many are just not yeah, thank you all.
Thank you so much.
Okay.
Yeah, so big hand to all the session speakers, and Dilip will take over from me.
So thank you very much thank you Kalyan sir for chairing the session. On behalf of the department, I extend our thanks. Even in your busy schedule, you have managed somehow.
I have to go into another meeting just now from here. Thanks a lot.
Thank
Thanks a lot,
you.
Dilip.
I thank the speakers, Professor Bruce Burnt, Professor K.R. Vasuki, and Gaurav Bhatnagar for delivering their talks in this session. And now at 11:15, we have the paper presentation sessions going on. There are two sessions, 10A and 10B. Those who are having paper presentations can join that session. And in the afternoon, we will be joining the Zoom link again at 2 p.m. for the session chaired by Professor A.K. Agarwal. And in that session, we have Professor Yuri Luchko, Professor Ilma Simshek, and R.K. Parmar presenting their work. So I request each one of you to join back in the sessions of paper presentations and coming back at 2 o'clock. So thank you very much for.
Okay. Bye.
Thank you, sir. Thank you very much.
Bye, Amma.
Bye-bye. Thank you, Gaurav.
We'll talk.
Thank you.
We'll talk on phone later.
Yeah, sure. And I hope this association with the SSFA will continue.
Listen, I'll tell you, I was there before the association.
Yeah. Yeah.
I told you that I attended that first conference in 1997, where there was a meeting saying that we should have an association.
Right. Yeah, it started from there only.
From 1990, yeah. So
Yeah. The idea came in that conference only.
Was pushing
Yeah.
that everybody should have it. So
Yeah.
yeah, it's good to see it's grown so big and so
Yeah.
nice. Yeah.
Thank you very much.
Fantastic. Yeah.
Dilip, can you stay back for a few minutes? I have to discuss.
Yes, sure, sir. Sure. So participants, please join the paper presentation session. I think it's already just opened up. So go to the Google Meet for that paper presentation session.
Or we can talk on phone.
Yes,
Yeah.
sir. That's
Okay.
fine. That's nice.
I'll call you.
Okay.